I'm gonna enter in the quantum information thing. So the first thing we introduce a few measures of quantum information. What do we mean by quantum information? And then distances, and then a very important, extremely important quantity called the whole level quantity, whole level information, which bounds the amount of quantum information can transmit. Okay, bounded the amount of classical information transmit. Quantum information is a different thing. So, do you remember in the first lecture where we defined the bit, that Shannon introduced the meaning of a bit? Physical Shannon made a difference between the physical bit and the logical bit. And the theory is all about the logical bit, which doesn't depend on the implementation. Here you have the same thing, but here you have the logical qubit, which is independent of the implementation of the logical qubit, which can be a superconducting atom or a two-level system or anything like this. Here is just the basic quantum system, the simplest one, which is a system with two levels that we denote in the computational basis. That's the base that we use in entire quantum information thing, by 0 and 1, by these cats. Here it doesn't really matter what these guys are. It can be currents, it can be whatever we want. This is not important here. The first difference that you have here is that the qubit, as you know, can be in a superposition of states with this because of conservation of probability. This implies that you cannot use more Boolean algebra to do computation. We need to use linear algebra. Otherwise, because Boolean algebra doesn't allow for superpositions. So we need to change the language. That's the first difference. There will be many, many more. The way in which we can visualize a qubit is, since we have this thing, we can parameterize the qubit, general state of the qubit with two angles, which are the Euler angles of this guy. And this is the Blois sphere, as you all know. So this is the 0, this is the 1. Here is a superposition in the y direction. Here is a superposition in the x direction. This is the plus in x direction. This is the plus in y direction. This is 0 and 1, which is the basic qubits. And we can, one difference that you have here is that we have infinitely many pure states for the qubit, although only 2 of them are orthogonal. I can only distinguish 2 of them. This is very important, for instance, for cryptography, because it's based on distinguishability of a quantum states. But a coin, a classical coin, classical bit, the parameter space of a classical bit is just a line. No? This is tails, this is heads, which are the pure states of let us call pure states of the coin, while the pure states of a quantum bit lies on the surface of a sphere. So this implies a very, very important difference between these guys. That classical probability theories, all the probabilities that is allowed by classical laws of physics, they form what we call a polytope. A polytope is just the convex roof of a finite set of points. That's a polytope. These finite sets of points are the pure states of the probability distribution. Everything here are just combinations of this guy, mixing of these guys. That is different. The quantum mechanical probability distributions are not a polytope, because you have infinitely many pure states. So we have infinitely many points. It's the convex roof of infinitely many points, like the surface of this sphere. If I establish a coordinate system in which the coordinates are the probabilities here, the equation of this plane is what we call Bell inequality. So this is a Bell inequality, this is another Bell inequality, we have infinitely many. That splits the local polytope from the quantum correlations. That's the physical meaning of baryon equalities, or the mathematical meaning. I mean, it splits the polytope from this guy here, which contains non-local correlations. That I call it non-local for historical reasons, but they're actually local. Okay, is that that's the meaning of baryon equality? That's one of the differences between the parameter space in classical probability distribution and quantum probability distributions. They are absolutely different. And one question that we don't know how to answer is that mathematically speaking, we can have bigger things than this. I mean, baryon equality, the simplest one, which is for 2 qubits, you can violate it up to 4. But quantum mechanics violates it up to 2 root of 2, which is Tiras's bound. Nobody knows why. Nobody knows why we can't have stronger correlations than this. This is an unanswered question yet. Even though we could have, but nobody understands why that is a Tiras's bound. So it's a nice problem to work, but it's a mathematical problem. It's just mathematics. You understand the stronger of correlations, and why quantum mechanics doesn't allow for us to have stronger than this. So, questions? No. I'm saying a bunch of things here that are quite complicated, actually. So, as you know, you work in quantum computation, quantum algorithm, and things like this. Quantum entanglement is one of the most important researches we have for these things. I mean, the advantage of quantum stuff is supposed to come from this guy, from quantum entanglement. So, a bipartite quantum entanglement is quantum entanglement state is the one that cannot be written like this. Inseparable. Let us take to the pure state, okay? And one of the main tools we have to analyze quantum entanglement states is the Schmidt decomposition, that I think that everybody here knows. Does anyone never heard about this before? Oh, no, okay. It's a very nice statement because it says that every pure state can be written like this. These guys are real and positive numbers. The number of these guys is what we call Schmidt rank. So, in the notes that I will upload, I pretended to upload it today or tomorrow, I proved that this is the case. And any system can be written like this. So it's proved there, you don't need to worry about the proof. It's there. It's basically a restatement of the singular value decomposition. It's not that difficult. It's very simple, but you can write always like this. So every state can be written like this. These are orthonormal eigenbases in the space of A and B. And the set of lambda with the set of Schmidt coefficients fulfills this condition. And this is an interesting thing because the number of Schmidt coefficients is the minimum between the dimension of this guy and this guy. It's smaller than or equal to the minimum. This is a very interesting thing because it says that, let us suppose that we have a qubit here. And here we have a system of dimension, 1 billion. This says that I just need a vector in a 2-dimensional subspace of this guy to describe the state of the system. You see? I mean, how strong is this statement? But it's true. I mean, it's easy to prove. It's just a singular value decomposition. And the number of these guys are the Schmidt. D is the Schmidt rank. If D is equal to 1, the state is separable. Because we only have one of these guys, and then you have these and these. Oh, no. It's not entangled here. No? Yeah, it's a typo. You see? Because, I mean, if I put just one here, I have cleared a product state. So there is a base that's a product state, so there is a typo. He is not entangled. If I have two of them, it's entangled because these bases are orthonormal, so they are entangled. That is no way. Okay? So this is Schmidt decomposition. This is one of the basic tools we have to study pure state entanglement, bipartite pure state entanglement. Okay. Okay, distances. Distances are a very important notion because we are interested in quantum information protocols like quantum computing or algorithms or whatever. We need to process information. Processing information usually is a noisy thing. Like when the computers have noise, we cannot avoid these things. So we need to understand how to know how well a given process is going on. And the way to do this is through these distance measures. There are plenty of these guys. Everyone is, appropriated for some process that you are interested. There are many relations between these guys, mathematical relations, but every one of them makes the same thing. It gives you a way to compare quantum operators or quantum states. And the first one is called the scatter one norm, which just defined it like this, where this absolute value of the operator O is this guy, which is not always easy to compute because the square root of matrices are kind of complicated to compute, but usually, we can do this on a computer, and that's okay. That's the scattering norm or the trace norm. So there are several properties. One of them that is always it is proven in the notes that I will put to you there, is that this guy is equal to the sum of the singular values of the operator. So you use the singular value decomposition, you just compute the singular value decomposition of this guy, pick up the singular value, sum, you have the trace norm. That's not difficult to prove. Yeah, and it's a very nice relation because usually it's easy to compute the singular value decomposition of a matrix. So you just build the representation of this guy and then compute it. It also satisfies non-negativity. This is easy to show because these guys are positive numbers, so this guy cannot be negative never. They are singular values of a positive operator, and homogeneity and triangle inequality. So these classify these guys as metric. So this is a real metric.
I think there is an equal sign instead of.
Sorry, come again. Which equal sign?
The inequality.
Oh, here is an inequality. No, yeah, no, oh, yeah, triangle inequality. That's, yeah, it's a typo, sorry. So two typos I need to correct. But this is the inequality here, of course. But this is the property that define a metric here, a real metric. So this guy different from the distance that we saw in classical theory, which is the relative entropy. Relative entropy doesn't fulfill the correct form of this equation with inequality. Okay. Please, guys, if you find more typos there, just let me know that I've corrected, upload the correct file. Okay. Some other important properties is isometric invariance. This is usually very important. This is isometry, just a unitary transformation. It's easy to prove this thing because of this. Unitary transformation doesn't change the singular value, so it's the same thing. It's invariant. The convexity, it comes from the triangle inequality. And variational characterization. This is a little bit more difficult to prove. little bit more tricky, but also is easy it's not so complicated. It is detailed in the notes. So it is not that important. This is a thing that we always use in quantum computation, quantum information, or things like this, which is the trace distance. No, this was the trace norm. From the trace norm, we can define the trace distance, which is the difference between two dense operators. That usually we want. This is usually the theoretical prediction that we expect, and this is the one that comes out of a quantum computer, for instance. So we want to understand how well how close these guys are. So if this guy is maximum, which means this guy here, then there is a single measurement that can distinguish between them. If it's zero, it means that there are no measurements that we can distinguish between these two guys. So that's the basic idea of these trace distance thing. Oh, we start at 10:30. Oh, that's okay. Okay, there is an interpretation of this guy in terms of hypothesis testing. Hypothesis testing is just like this. LSC has to distinguish between two quantum states. This guy and this guy, who are prepared with the same probability distribution. So uniform probability distribution. Bob prepares this state by tossing a coin and send them to LSC, and LSC has to perform some P of M, binary P of M, and to guess which one is the stage. So this is the basic scenario of hypothesis testing. And we call the result of this P of M as the random variable Y. Okay, that's the basic scenario. And we can compute the success probability. The success probability is just written by this, which is the conditional probability of preparing 0 and getting 0, and the conditional probability of preparing 1 and getting 1. But these guys are equal to, this guy and this guy are equal to 1/2, and this guy are equal just to trace of the operator times the measurement operator. So, since these two guys must sum to identity, we can write this thing like this. Okay, and this is just the trace norm. Sorry, typo here. This is not the trace norm.
Isn't there, I think there's a measurement missing maybe?
No. That thing is correct. That thing is correct. This is a type of by copy and paste. Here is not correct yet because this side you see depends on the measurement. This doesn't. So this cannot be true. It will be true, but not like this. So just cancel this part, and this part is correct. This is correct. This is it explicitly depends on the measurement we choose. But LSC wants us to maximize this guy because this is the probability of her correctly guessing the value of this random variable. So he wants to maximize this. And how she does this, just maximize over all possible P of M's. And then the probability of success, the maximum of this guy, and then this equality is correct. Then it's possible to prove that the maximum of this guy is equal to this guy. Then it's independent of the measurement. Then this is correct, and this is the trace norm, or the normalized trace norm, because now this quantity varies between 0 and 1. So you see, when this guy is 0, LSC has no possibility to guess correctly guess the value of the P of M. I mean, it's just tossing a coin. When this guy is 1, then it has the maximum probability, and he always correctly guess the value of the random variable, the outcome random variable. So that's the interpretation of this guy in terms of hypothesis testing. It quantifies the probability of success of your protocol. Okay, so every measurement, every measure that you, not measure that we see here will have some operational interpretation in some protocol. Everyone. So just need to find the correct one, but everyone has. Sometimes more than one. Here you can also state this guy as the relative entropy here also. So a relative entropy also appears in the hypothesis testing scenario. And this is a very general scenario actually, because every physical experiment can be put like this. Every single one is a binary experiment. I think that yes or no. So this is extremely, extremely general. Okay. Fidelity. Fidelity is a different measure that we use. I think that everyone here knows these things. So this guy here is the fidelity for two pure states, simply defined by the overlap of these guys. So we can distinguish between them or see how close they are from each other. If this is equal to 1, they are the same state. If it is equal to 0, they have support on orthogonal subspaces. And then this has this Ullmann fidelity. By the way, how to say the name of this guy? Ullmann. So Ullmann fidelity. Ullmann fidelity. Okay, that's yeah. This is the most general fidelity measure that's just given by this guy, which is the trace norm again, appearing here. But then you have the square root of these guys, which is not, I mean, that easy to compute, especially if they, because usually these guys don't commute. So they cannot be diagonalized in the same basis, and compute these things a little bit tricky, but it's possible. And this guy has a very nice interpretation also, because it's related to the Boole's angle, which is the arco-cosine of the square root of this guy. The Boole's angle gives you the angle in Hilbert space between two vectors. Is the smallest angle that you have, is the geodesic associated with the Fisher information. If you treat Fisher information as a metric, what it is, the geodesic associated with this metric is the Boole's angle with the arco-cosine of the square root of this guy. So it's deeply known in geometric theory of information. Have you guys heard about this? I mean, we have the entire theory of information theory was reformulated in terms of differential geometry. And there is a theorem that proves that the space of all probabilities has a single metric defined on it, which is Fisher information, the classical one. And the space of all density operators has infinitely many metrics defined on it, which are the infinitely many different ways to state quantum Fisher information. So Fisher information is fundamental in this sense. But this is a different course. Then we go to the main thing of this topic, which is Shannon entropy. It's interesting to note that Shannon entropy, von Neumann entropy, was introduced much before Shannon entropy, because von Neumann entropy introduced in the 30s this guy, and Shannon introduced it in the 40s, the classical entropy. And actually, von Neumann told Shannon to call his entropy entropy, because at that time nobody really understood what entropy is. So this gives a meaning of the information of a logical qubit. It quantifies the amount of information that we have in the system, whose state is rho. And apparently it looks like the Shannon entropy, but is extremely different actually. It has very, very, very strange properties. And this guy that we will see now, a very important properties. Well, as you know, every density operator can be written like this. Because it's a Hermite operator, so we can diagonalize. It fulfills the spectral decomposition theorem. These guys are the probabilities. In this case, we have that von Neumann entropy is equal to the Shannon entropy of this van der Waals. Okay, that's easy, which shows that von Neumann entropy is positive and bounded. Because this guy is positive and bounded, this guy is equal to this guy, so it must be positive and bounded. And it's not difficult to show that this happens because of the Shannon entropy. It follows from the classical thing. Okay? Concavity also follows from Shannon, from classical theory. We can prove the same thing here and there. So it looks like that everything is the same. But they are not actually. This is a very important property that we will use today, later on. That's von Neumann entropy is invariant under unitar transformations, under isometries. This you already know. It's very easy to prove this, to show this. And we can extend this, then comes the difference. The main difference, one of the main differences between the Shannon entropy and the von Neumann entropy. Of course, von Neumann entropy can be written for a bipartite system. It's just simple extension of the case of single system. And then we can use Schmidt decomposition, because you can write this thing for a pure state like this, and you can use Schmidt decomposition to write the state like this. And then we just compute the marginals of this guy, of A and B. The marginals of this guy are these and these. It's easy to show them, it's easy to compute. What's the important thing that you have here? These bases are different, but they have the same eigenvalues. So the marginals have the same eigenvalues. Which means that the marginal entropies are equal. Because the entropy of this guy is equal to the entropy of this guy because they have the same eigenvalues. So this is important, a statement. But what's the entropy of the entire system? Well, the entire system is pure. This guy has one eigenvalue, which is equal to 1. So von Neumann entropy of this guy is 0. What we are saying here is that although you have marginals here that can be different from 0, and usually they are if the state is entangled, you can see that if the state is entangled, you have at least two of them that are not 0. So the entropy of these guys will not be 0. It will be bigger than 0. Actually, if they are maximally entangled, then the entropies will be maximal. The marginal entropies will be maximal. This means that we know everything about the global system, but we know nothing about the individual parts of the system. That's what's written here. This is impossible in classical physics because classical entropy, joint entropy, fulfills this inequality. So in classical physics, if we are uncertain about the global system, we can attribute this uncertainty to local systems. In quantum systems, you cannot do this. This means that it's impossible for an entangled state, it's impossible for us to assign an individual state for each one of the subsystems. This is entanglement. This is entanglement, and this was written in Schrödinger's paper that I recommend everyone to read that paper, where he described entanglement like this and called it this as the fundamental characteristic of quantum mechanics. And this is the first main difference between von Neumann entropy and Shannon entropy, because of the characteristics of the quantum system. Okay, is that clear? And you see that they are exactly equal. This is the measure of entanglement. For pure state, this is the only entanglement measure that you have. the von Neumann entropy of the reduced state. But this is independent of the way we do the partition, make the partition of the system. So we have, let us call this A, B. But I can do another, I think that this one, yeah. Yeah. You see?
There's a trick of taking a erasable marker, drawing on top of that, and then you can erase that.
Okay, okay, that's okay. But you see, this one I can, yeah. But I can do another partition here, and these things, these equation, the first equation is 2 hold. What's the meaning of this? That this guy should not depend on the volume. It must depend only on the things that are in common between the two subsystems, which is the area. That's why entanglement fulfills area law and not a volume scaling law, like the thermodynamic entropy, for instance, because of this equation. You see, so it's completely different from the classical way we understand uncertainty, because this is still a measure of uncertainty. So the uncertainty of the pure state, that's an S missing here. Of course, rho AB is not 0, but S for rho AB is 0. The entropy is 0, which means that I'm perfectly certain about the state, the global state of the system. And this is okay because, I mean, if I know the state, we have quantum fluctuations there, of course. But the problem is that if I know the quantum state, I can perform a very specific measurement in which I confirm that state. I just project on the basis in which the quantum state is one of the elements of the base. Then the probability of getting out that state is 1. So I learn nothing by measuring this thing. That's why the entropy of the global state can be 0. It doesn't. I learn nothing from measuring this guy. But the entropy of the joint, the marginals are not. And then this is entanglement. And this is another very, very strange thing, the conditional entropy. You remember that in the first day I introduced the classical conditional entropy, and it was positive, and every fulfilling every nice property that an entropy should fulfill. Like we just extend, instead of H, we put S, which is the von Neumann entropy, and this is mentioning that it is a rho here, depend on the state of the system, of course. This is not important in classical physics, but in quantum mechanics it is. These are all quantity depends on the states. And it obeys an equation like this. Conditioning doesn't increase uncertainty, which is, I mean, the same thing that we have in classical physics. But let us consider this guy, which is one of the Bell states. This is an entangled state of 2 qubits. And when we compute this guy, rho A and rho B are equal to the identity, maximum mixed state. This entropy is 0 because the state is pure. This guy is 1. So the conditional entropy of this guy is -1. So it can be negative. And this fact is so important that it has its own name, which is this guy is a measure of quantum correlations. Usually in the books you see this guy in a different notation, which is I, A, B. But I don't know how to put this symbol in LaTeX, so I put it that one. Okay. But in books you usually encounter this symbol, which is just the negative of the quantum quantum conditional information, which is a measure of the quantum correlations that we have in the system. Do you remember that the classical mutual information was a measure of the total correlations between two systems, two subsystems in classical system? Here we also have the quantum mutual information, but the quantum mutual information is a measure of total correlations that you have in the quantum system. But this guy measures only the quantum part of these correlations. In this case, since the global state is pure, it has one bit of entanglement. It is entangled. The state is entangled. That's the meaning of negative entropy, because the state is entangled. So we define this quantity called coherent information, and this, if I have a quantum channel, the capacity of the quantum channel is a maximization taken over this guy, not on the mutual information, but on this guy. I will detail this in the notes. I will not bring here the theorem because the theorem is quite more complicated than this. But these guys is deeply linked with the quantum capacity of a channel. So it's extremely important the fact that this guy can be negative. Is this for entire quantum information thing. So these are a fundamental difference between quantum and classical information theory, and this is because we have a stronger correlations than are allowed by classical physics, by the classical laws. Okay, just mutual information is defined exactly the same way. This is a minus sign here. This is minus. Because we have the uncertainty in one system, the uncertainty in another system, minus the global uncertainty. This gives us the total correlations. If we compute this guy by this phi, the same stage, the same Bell stage, then this is equal to 2. Why? Because we have one bit of entanglement, which means conditional entanglement is conditional entropy is minus 1. So we have one bit of entanglement, but we also have one bit of classical correlations between these guys, between the two qubits. So that's why this guy is 2, but we have just one bit of entanglement, which means that I can transfer, I can use it to send the state of one qubit via teleportation, for instance, but just one qubit, not 2. Okay, this is the mutual information, which is a measure of total correlations. And then one of the most important quantities we have in quantum information theory, which is the quantum relative entropy, which is this guy over here. We just need to take care about the support of these guys, because it can be infinite. If the support of these guys is not contained in the support of rho, this guy goes to infinite. But it's the same reason that we discussed when we talk about the classical version of these guys. Okay, this guy is extremely important quantity, and this is one of the most important inequalities in the entire information theory, which simply states that under any quantum operation, relative entropy is monotonic. Under a general and a general process, relative entropy is monotonic. So we cannot increase the distinguishability by processing the information. This is not possible. By process information does not increase the distinguishability between the states. That's one of the fundamental inequalities that you have here. And you can prove that if you put it here, a thermal bath, for instance, the action of a thermal bath on a system, this map has a fixed point, which is the thermal state. So this guy goes to 0, and this distinguishability goes to 0. That's thermalization. So this thing is used in several areas of not just information theory, but physics and chemistry and neuroscience and a bunch of other science, engineering. So this is extremely important. And this is a nice relation between the relative entropy and the trace distance, which is called the quantum Pinsker inequality. We have the classical Pinsker inequality also, it's a little bit different, but related. So that's the quantum Pinsker inequality. It's very useful for doing calculations. Since this guy usually is difficult to compute, but this guy is much easier to compute. Remember that is just equal to the singular value of the composition, singular value, the sum of the singular value of this guy. So it's usually easier to compute than the relative entropy. And sometimes a bound is what we need. We don't need the full thing here. Okay, coherent information. Coherent information, it's just what we defined before as the negative of the conditional quantum entropy, which is extremely important. And this is the quantum version of the data process inequality. We have several of them. Actually, every measure of this thing fulfills a data process inequality. Here, just the most important ones, because this guy, as I told you, is related to the quantum capacity of a channel. And then this guy is important. It simply says that when I apply, remember that this thing here implies directionality, and this thing I just need to apply to the second one, because the second one is the conditioning part. So that's why I just need to apply in the second part. It's the part that I am conditioning the system. So it's just a quantum channel, which can be whatever, can be unitary, can be whatever, that changes the state of the system from rho AB to sigma AB prime. And then the data process inequality for coherent information, that's the stages. Stated is, I mean, it's easy. It decreases, reduces correlations. There is no way to increase correlations, because this is a measure of quantum correlations, so the quantum correlations are decreasing. There is nothing you can do to increase this thing by processing information. There is no way. That's the meaning of this inequality, which can be also stated for the mutual information, which means that quantum information decreases, quantum correlations decrease, and total correlations also decrease. Everything decreases. So classical and quantum correlations decreases when you process information. At most, they stay the same, but they cannot increase. Okay, that's the statement of the data process inequality. It's exactly the same meaning that we have in classical physics. But in classical physics, we don't have this thing. In classical information theory, we don't have this thing. We just have classical correlations. So that's easy. And he has a very important result about these things that puts a bound on these guys. That's whole-level boundary. Whole-level boundary, you remember that the classical capacity of the classical channel is the maximum overall probability distributions of the input channel of the mutual information between the input and the output. Let us write this with this one that I can erase actually. So, X is the input of the channel, that is called channel. Y is the output. That's the classical capacity of the channel. It's the maximum overall probability distributions of the input of the channel, of the correlations between the input and the output. So this guy is extremely difficult to compute. I mean, it's extremely difficult because this maximization, this optimization problem is horrible. So in general, we cannot compute this guy. But this guy, Alexander Holevo, put a bound on this quantity, which is easy to compute. And this bound is the Holevo bound. Let us suppose that the LSC prepares this guy, which is just, the ensemble that she's putting as an input of the channel. Of course, Bob doesn't know the probability distribution, but they know the mathematical description of the channel. This is possible to do by throwing known states and measuring the output, and then you can estimate the conditional probability that describes mathematically the channel, This is perfectly doable. So Alice prepares that ensemble and sends it to Bob. Okay? And Bob has to find out the value of X. How? By making measurements on the output is the only way that he can get this information. So, but for Bob, the state of the system is this. Because Bob doesn't know the value of X, so that's the state that Bob, that's the mathematical representation of the state that's coming out from the channel for Bob. Okay? And then Bob performs some measurement on this state and has to guess the value of X. The maximum information that we have, that Bob have access, is called in quantum information theory the accessible information. Okay, which is just this guy. That's, as we saw in Shannon, as in Shannon theory, you know, this is a classical random variable. It's not a quantum one. So this is exactly this equation here. Because I'm maximizing over all the probability, all the measurements that Bob can make. So I maximize the information that I can get, that Bob gets, and this maximum should be this guy. Cannot be bigger than this because Shannon proved that this cannot be done. So it must be this guy. What Holevo proved is a little bit technical, but it's not that difficult to prove. That you have in the handwritten notes there. Holevo proved that this quantity is upper bounded by what is called the Holevo quantity today of the channel, which is just the von Neumann entropy of the state of Bob, of the state that Bob has there, minus this quantity here, which is the average von Neumann entropy of the guy. So this thing is very easy to compute. And then, although we cannot compute exactly this quantity here, we can compute this guy. So we have an upper bound on the amount of information that we actually have. And this is an upper bound on the amount of information that can be communicated through a quantum channel. You cannot do better than this. And this is known today as Holevo bounded, and this guy is the Holevo chi quantity. This is a very important result because it allows us to compute things, actually compute something that usually we cannot. This is, I mean, is not computable for most of the channels. It's simply too difficult to perform this maximization because the number of parameters here grows exponentially with the dimension of the system. So this is extremely hard, but this is very easy to compute. So that's the famous Holevo bound. Okay, and rho bx is this quantity here. Is the ensemble that LHC prepares. Because LHC has a probability distribution where I have several rho b's and No. The results of measurements are the y variable here. That's the result of Bob's measurement. No. So, meaning of von Neumann entropy. Remember that. So this is the last thing that I'm doing in the notes there. Everyone else is also written there. I'm proving now the converse of this theorem. Then I will update it there. But the theorem is quite complicated, so I'll not show it here. It's not that important. But the meaning of this is important to show because this gives meaning to von Neumann entropy. Do you remember the classical data compression theorem? Classical data compression theorem says that we can compress information at the rate that is at most smaller or equal to the channel entropy of the source, of the information source. So that's the maximum rate that we have. Rate of compressing information. Here we have the same thing, which is called Schumacher's compression. It was proved by Benjamin Schumacher, which is the quantum data compression theorem. So it's the same thing, but the protocol is a little bit more complicated. I'll show the protocol here, and I will upload the calculations of this guy, detailed calculations of this guy. The techniques are very different from those who use it to prove the classical data compression theorem, but it's understandable. Let us see what the theorem says. So the protocol is characterized by this guy, like the classical one. The number of times I used the quantum channel for compressing information, so I'm doing quantum compression now. R, which is the rate that I want, and epsilon with the error. Okay, and the same thing as the classical thing. And then we have 4 steps: preparation, encoding, transmission, and decoding. The same thing as there, but they are quite different now. The preparation of the quantum state says that we have information source that is emitting quantum information, now represented by quantum by state vectors, with this probability distribution, it is ensemble here. So a sequence now is not a sequence of letters, it's a sequence of state vectors like this. And this is huge, Hilbert space, because we are emitting quantum states over and over and over, and these guys have to go to infinite to prove the theorem, but anyway, it's the same thing. So for someone that doesn't know these things, the state of the system is going to be this guy, the tensor product, the n parts tensor product of this row, but this row is simply this guy. Okay? That's the information source is emitting these symbols. So these are the symbols, and this is the state of the symbols that describe this system, and this sequence of symbols. And then encoding. Alice has to encode this guy, this system, which is a huge system, like the data compressing, the classical data compressing theorem, that Shannon let the source to emit a huge sequence and then compress it at all, as a block. These allow him to prove the theorem. So he chooses some encoding channel, any encoding process that they want to use, that takes you to from this guy to this guy, where W is a quantum system of this size, because it's the rate of compression, and this is the number of times that I will use the channel, the quantum channel, to transmit the information, this information here. So it's the same thing as in classical data compression, but now these objects are different. And the rate is given by this guy, because this is the size of the system that I want to transmit. This is the number of times that I have to use the quantum channel to transmit my information. So this is the number of times I use the channel, and this n is the size of the sequence. It's exactly the same way we defined a rate of compression in the classical case. But the number of sizes is the dimension of the space, which is exactly the same thing there, except that this guy grows exponentially with the number of things, of objects that you have here. In the classical case, this doesn't happen. It's linear. But anyway, it's the same. The idea is the same of defining this guy. Is that okay? No questions? No? Okay. I'm just doing data compression, but with quantum things. Then transmission. I'll just send it over to Bob using n times r, the quantum channel. So that's how many he used. And then Bob decodifies this thing by this decodification channel, which takes W, which is the output of the channel, into the AN, which is the sequence that he wants to understand, to reach. And then the error is characterized by this guy over here. So that's the theorem. The theorem states that the error is characterized by this guy. And the compression rate is achievable And this is the trace norm. Or actually the trace distance, because the distance between the input state and the codification one. If these guys are equal, this is 0 and we have no error in the compression. Okay? So the compression rate is achievable if there exists these guys with these positive numbers here and sufficiently large n, which means the asymptotic limit of the theory also. And then we can achieve this rate. The quantum data compression limit of rho is equal to the infimum of all achievable compression rates, which means the infimum over these guys. You see that's extremely difficult to compute these, but anyway, that's, as always in information theory, we define a bunch of things and they are practically impossible to compute. But is this. The important idea is that the error is characterized by this trace distance and the quantum data compression limit of this stage, which is this guy here, is equal to the infimum of this quantity. Okay, that's Schumacher's theorem that you get proved there, and this is the first statement. And then the converse theorem, that is the thing that I'm putting there now, proves that this rate is optimal. There is no way to choose D and E here to get things better than this. There is no way to do this. So that's the quantum data compression or Schumacher compression or Schumacher theorem that you found all of these terms in literature. And then we come back to the meaning of von Neumann entropy. Suppose that rho is the density operator corresponding to a quantum information source, which means that the information is emitting this guy here. The quantum entropy is equal to the quantum data compression limit of rho, which is exactly the guy that appears here. So this means that von Neumann entropy characterizes quantum data compression in the same sense that the Shannon entropy characterizes classical data compression. So that's the maximum rate at which I can compress quantum information, and Shannon entropy is the maximum rate I can compress classical information. So that's the meaning, the operational meaning, let us say this, of the von Neumann entropy given by Schumacher's compression theorem. Okay, so it's the same thing as in classical data compression, but as we saw, this guy has properties that are very, very different from the Shannon entropy. Although they are closely alike, but they are extremely different. And this is the meaning that well, of course, we have others meaning like uncertainty or things like this, entanglement is entanglement measure, but this is the most known operational meaning of this quantity inside information theory. Okay, it's the informational meaning of this guy is the data compression rate, quantum data compression rate. Okay, and this is given by Schumacher's compression theorem. Of course, we have another theorem that is the capacity of the channel, but then we have classical capacity of quantum channels, which is given by this guy. We have quantum capacity of quantum channels, which is given by a maximization over a maximization of the coherent information, which is a different thing. That's the thing that I will prove there for you. It's a thing that we only have in quantum mechanics. In classical physics, you don't have these things. And with 2 minutes late, we finished this first part. Okay, so questions, please. We will now apply these things, especially Shannon entropy.
Maybe this quantum version of the compression theorem that we just talked about. Yeah, is there also the notion of typical sequences here in the quantum version, or?
Yeah, it's there, but it's a little bit different. But I mean, you need I mean, you cannot compress every guy like this. That's is going to be impossible. If you have to compress everything, then nothing happens. You compress nothing, and but this will happen when this guy is uniform. Then you have to compress anything. There is no typical sequence. Every sequence is typical. Like tossing a coin. Tossing a coin, a fair coin, every sequence that I get is typical. I have to compress anything. And that's why we say that it's impossible to compress truly random variables. But in general, we don't have this. In general, this guy is some sort of Gaussian or something like this. So we must have some knowledge on the probability distribution in order to quantify. But that is a notion that's like the classical typicality, which is called the quantum typicality. And this is involved in the proof. The techniques of proving is different, but the idea is basically the same.
Y en cuanto utilizas el clásico humano, es una theorem some theorem is there in the limit but not achieved.
Well, the theorem says that basically there is a code that you can achieve that rate, and this code is optimal. But or not in the classical or the quantum system, no one says how to find out which code is this. Like I said, information theory, you define a bunch of things, prove a bunch of things, but they are mostly uncomputable. Yeah, it's extremely hard to compute. That's why whole level bound is important, because we can compute upper bounds on this thing very easily. So results like whole level bounds or inequalities are very important because of this. That's why you have a bunch of inequalities in information theory. A bunch. Because we actually cannot compute the equalities, so we have to use inequalities to at least have bounds on these things. Well, of course.
How do you see, because the follow one, the way that you have explained it is like a communication channel.
Yes.
But how do you understand this in terms of measurements, for instance, in quantum computing? So the maximum information that you can extract from predictive measurements is an EHU system is a bit. How will you obtain this from this expression?
Well, whole level bound is stressed that, let us say that we have the X is the input, and then Y is the output. Y is the output of the quantum computer. So I want to extract information from this guy. So the entire quantum computer, the entire quantum circuit can be treated as a channel. It can be a unitary channel if it's perfect, or usually it will be a noisy channel because there are noise there. Then we can actually compute this quantity here. But this is a maximization over all possible measurements, not only projective ones. But there are some works that the guys studied this quantity, the whole level quantity, under the restriction, well, actually this quantity here, with the accessible information, when you have access only to projective measurements. But I don't know how far they went, but there are. So if you don't have access to, now this is the important thing about von Neumann entropy. Von Neumann entropy assumes that you are able to perform every possible measurement on the system, which is not true in general. You simply cannot do this. If the system grows larger, you cannot do this. I mean, you have access to a very few measurements. Usually just the energy is the only thing that you can measure. So that's why Mikko is asking this, because, okay, these I'm maximizing over all possible measures, so this is the best thing we can do. But we can compute this quantity restricting this guy to projective measurements, and then it's much easier to compute this maximum quantity here using just projective measurements. But it's going to be smaller than this guy for sure. At least for very specific cases where the best P of M is the projective one. But usually it's going to be smaller. But then we can make some calculations depending on the case, because averaging over projective measurements is much easier. It's not easy, but much easier. Then depending on the case, it's possible to compute this guy. We saw classical information theory, and then we saw an application of classical information theory to solve a classical thermodynamic problem. Now we saw a little bit of quantum information theory. Now we see the application of quantum information theory to solve a quantum thermodynamic problem. Okay? I decided to apply to do the applications in the middle of the cursor, because it's easier instead of showing a bunch of calculations here and then applying things. So, by the way, does anyone knows what Pequi is? Pequi. It's a fruit that grows in the place where I live, and it is a very characteristic flavor and taste, and we put it everywhere. We make ice cream, food, everything. This is amazing. It's unbelievable. This fruit. I really love this thing, and that's why the group is called the Quantum Pequi. And this is the shape of the Pequi. And the not here, but if you take a look at the web page, this is a sort of orange, which is the color of the Pequi. So that's that. It's really, really delicious. My wife hates, but I love. Okay. Irreversibility, guys. We're talking about reversibility here because we need to understand how reversibility comes in, and that's where information theory enters. Because all the fundamental laws of physics are reversible, which means that I can just change the sign of time and everything keeps the same. So one of the biggest problems that you have today is from where irreversibility appears. We actually don't know why a closed system thermalizes. A closed quantum system thermalizes. We don't know. Nobody knows the answer to this question. But the way we see today is simply a lack of knowledge. You don't know things. Thermodynamics comes in this way. In thermodynamic limit, fluctuations goes to zero, but you make coarse-grained measurements, which means that the measurements that I'm doing here, measures of space intervals, are much bigger than the characteristic space evolution of the microdynamics of the system. The vibrations of the atoms are in a scale extremely smaller than the scale that I'm using to measure this table, for instance. And the same thing happens with time. And since we can only measure space and time, then we are making averages. All the quantities, all the thermodynamic quantities comes out from this procedure, which is a coarse grading. Then we have the thermodynamics that is usually described in textbooks. Okay, this is the sort of things that we consider. So we are throwing away a bunch of information by measuring these things. So classical thermodynamics is a subjective one because we need this is not actually knowledge. If this is a lack of capability to measure systems. If I improve my measurement skills, I could measure the state of the system, and then I have everything. But this is not possible because the number of degrees of freedom is too huge. Quantum thermodynamics, there are several proposals for this, and we thought in the same way here. If I have the density operator, I have everything. But in order to have the density operator, I can compute von Neumann entropy, for instance, to have the information that guy has. I must be able to perform every possible measurement of the system. Otherwise, I cannot reproduce reconstruct the quantum state, and I don't have all the information. Especially because the quantum state has more information than the classical state, because the quantum state has information about the basis of the system. It has information about all the bases. So this is too much information. And that's why we choose this guy, a gauge principle, that I will not assume that you know this thing. I will explain what it is. But the job of this guy is to wash away this information. So I choose this gauge perspective in order to build a coarse grain in information space. That's the main idea behind this thing. And then to build thermodynamic quantities from this coarse grain in the same way we do in classical physics. So let us see how this works, but these are some references of other approaches to quantum thermodynamics. There are plenty of them. These are the main ones. Especially this one is very, very nice by Elliott Lib. It's extremely nice axiomatic approach to thermodynamics. It's basically logic. It's very beautiful. If you have interest in reading this paper, I recommend it, but it has almost 100 pages. Yeah, of logical statements. But it's beautiful. It's beautiful. Oh, it's Elliott Lib. So the general goal here of this theory. Yeah, I'll try to be fast. How these thermodynamic concepts like these guys can be defined when fluctuations are unavoidable. This means small systems, where I have classical fluctuations, thermal fluctuations, or whatever, or quantum systems, where I have, ultimately speaking, quantum fluctuations. We cannot avoid these things, so they are there, and we need to live with these things. Our approach is just, say, let us do the same thing. Not all information contained in the density operator is useful for us for the thermodynamic perspective. But of course, this information is useful for quantum information stuff. But for instance, a quantum computer today, we can only make projective measurements in the energy eigenbase of the qubits. We cannot do better than this. So the question is, given that I have this limited access to the information, what can I do? What can I say about the system? And most important, how can I characterize what's the important information, what's not the important information? That's where enters the gauge principle. So it's just ability of controlling the system. If I have a very low ability, like a classical physics, macroscopic system, I cannot control the microscopic degrees of freedom of this table, for instance. So I have classical thermodynamics. When I have a high one, I have quantum thermodynamics. But here we are assuming that you can measure everything. We actually can't do. So how can we get rid of this? Most of the information, we say that's redundant in this sense, because it's not important for us to compute the thermodynamic quantities like we say that the precise knowledge of the microscopic state of the systems, of the molecules of this table, they are not important for us to compute thermodynamic quantities. We simply don't care about them. Actually, we don't care about what are the laws of physics they are following. It doesn't matter if classical or quantum, we simply don't care. So this is what you call redundant information. But in classical physics, we know what we are talking about when we say about redundant information. It's just the microscopic description of the system. This doesn't matter for us. The velocities and the positions of the particles that compose the system doesn't matter. But in quantum physics, we don't know. We have the density operator and we don't know how to throw away the correct information. That's why the gauge principle appears. Because, I don't know if you know, but all physical theories today are gauge theories. All of them. I mean, the fundamental physical theories are gauge theories. Electrodynamics is the gauge theory of the U1 group. General relativity is the gauge theory of the Poincare group. That's how we see gauge theories. This gauge principle is fundamental in all physics today. So every physical theory is a gauge one. The simplest one is electrodynamics. How gauge works here? We have the potentials of the thermodynamics, the vector potentials and the scalar potential, which are just potentials in general. They have no physical meaning. I mean, you cannot measure these guys. They are just mathematical objects. And why we cannot measure these guys? Because we have a gauge freedom. We can choose infinitely many of these guys to describe the same field, which is the real thing that you go to the laboratory and measure things. So how we get rid of these infinitely many degrees of freedom to just the ones that we are actually measuring in the laboratory, like scattering amplitudes, gauge principle. We have a gauge symmetry that links all of these potentials, and the gauge transformation simply takes us from this set of infinitely many things to the set of physical quantities. There are those that are invariant under the action of the symmetry group. So we build a gauge theory of the symmetry group of the system. That's the main idea of the gauge invariance principle. And then we thought, oh, let us do the same thing in thermodynamics. We have the set of all dense operators that have all the information of possible information. And then the information of these guys measured by the von Neumann entropy that we just saw. And then we must build a group, a symmetry group, that gets rid of all the information that's redundant here and takes us to the physical quantities that we measure in the laboratory, which are the thermodynamic variables. And why gauge? Because gauge, the job of the gauge principle is to do exactly this, get rid of redundant information. So we need to build, the idea is to build a thermodynamic group and then to build thermodynamics as a gauge theory of this group. That's what we have done. This is just a book about the gauge theories, but it's just for if one of you are interested in this thing, which I do not think that's the case. I mean, let us think here just this is an important principle in physics, and we apply this to the information theory and build an information group. That gives me thermodynamics. That's the idea. That's why we are using gauge principle. So don't think too much about what's the meaning of these and how can I construct these theories, but it's not important. I'm just applying this physical principle to the information theory. So the first thing is that we assume in the theory, every relevant quantity can be expressed as a function of the density operator. Well, this is not a big assumption. It can depend on other things also, the Hamiltonian or whatever, but in a sense, it will depend on the state of the system because, I mean, the information is there. So every physical quantity must depend on this guy. One special quantity is this guy with the energy of the system. So this guy we use everywhere because in a quantum computer we measure this guy, for instance. So that's why that thing that I'm studying now, the variation of quantum algorithm, hybrid classical quantum algorithm that I'm studying with David. The guys usually want to minimize this quantity. So this is a very low quantity. And also this quantity of work was proposed by Robert Alischik many years ago as a generalization of work into quantum systems. If you take a look here, it's just the derivative of the Hamiltonian with the expected value of this guy. So this is just the power. It's like integrated power, like we have in classical physics. It's just a straightforward generalization of this guy. So it's usual, but it doesn't work in every situation. But it's is a very intuitive definition. So, the potentials in the electrodynamics are the ones that can be transformed through the symmetry group that are not gauge invariant. We take this guy, rho here, as to play the role of the potentials. But these guys are in the information space because they have the information there. And it chooses the transformation to be unitary. Why? Because, as we just saw, von Neumann entropy is invariant under unitary transformations. So I want the group to be unitary because I don't want to change the information in the system. Because if I perform here a transformation that changes the amount of information that I have in the system, then I can change how much I can predict quantities. And this is we cannot do. So that's why this guy should be unitary. But this is not enough. This quantity, we know that the average energy, we know that must be equal to everybody. So we impose that these unitaries should preserve the energy. This is a strong imposition that implies that these guys should commute to the Hamiltonian. This is very, very, very strong. But otherwise, different people will see different energy, which cannot be true. So we pick up the entire set of these operators, and the group will give us just a small subset that contains the same, that everybody that will measure the energy of this guy will compute the same average energy. So all of the density operators there will give me the same average energy. That's the same thing that we do in classical thermodynamics. We have a probability distribution of microstates, and all the microstates have the same energy, or the same average energy. So, and there is a connection between these microstates. For instance, the microcanonical ensemble says that I have a surface of a sphere, where all hypersphere, where all the points on this surface gives me the same value of the energy. Here we have the same thing. We reduce the group reduces the number of density operators to a subset that takes us to the same average energy. But they are different, but they have the same average energy and the same amount of information, because von Neumann entropy doesn't change inside this subgroup because the transformations are unitary. So I impose this thing. That's why I'm imposing these restrictions. It looks like that is trivial, but not. I will not show here how to do this. Of course, I can discuss with any one of you if you want. I will not even put these calculations into the website. They are in the paper. But if any one of you is interested how to derive these things, I can happily show to you how we derive from these assumptions. We derive the thermodynamic group. That's the thermodynamic group that we have. So we have a group that's a subgroup of this guy, is the group of unitary matrices of d by d dimensions. This is a very important thing, and age is the Hamiltonian of the system, and then we have these relations. It can be written like this, where this u here, small u, is the matrix that diagonalizes age. So since this guy must commute to the Hamiltonian, then this guy is the most general form of this matrix. Okay, we cannot have a different form, and these guys here are the multiplicities of every eigenvalue of the system. So it counts the degeneracies and whatever we want. Then I'll also not prove this, but believe me, it's possible to prove that this guy is isomorphic to this guy. This guy is very strange. I mean, to work with this guy is strange. It's complicated, especially because we want to define the higher measure of this guy. But once you prove that this is isomorphic to this guy, then the job is done, because this guy we know. I don't know if Sri lemma. We didn't use Sri lemma to prove this, but oh, maybe it's easier. Oh, why I did a more difficult calculation? We proved it by using other things. Okay, but yeah. But I mean, it's possible to prove. Okay, and then gauge theory. This is gauge theory. Gauge theory. We have a functional of every quantity, every physical quantity that I want, like electric field or whatever, it doesn't matter. That's the way we define invariant quantities in any gauge theory. It's just group averaging. Anyone, these quantities is obviously it will be invariant, but it's also not difficult to prove that every quantity that you write like this is invariant. So if it is f is not isometric invariant, or it's not invariant under unitary transformation, we do this, and this is the Haar measure of the group. That's why we need to define this guy, and that's why this isomorphism helps a lot, because I know the Haar measure of this guy. But this one I don't know, but this one I know. So I can define integrals over the group, and then I can define invariant quantities. And if f is invariant under unitary, like the entropy, like von Neumann entropy, then we write down this guy, where this operator is this guy here, is the average of the group, and this whole EDD is can be written like this. That's the multiplicity of the eigenvalue k at time t, which means that it can change over time. I mean, this will change the Haar measure. The Haar measure here, if this guy changes with time, the Haar measure here changes with time, but this doesn't matter. Look that this is not the evolution. It's just a gauge, it's just a symmetry transformation that I'm doing at time t. The evolution is a different thing. The evolution acts on rho, it can be whatever. It can be non-unitary or whatever you want. So this is an averaging. So this is, what this thing is doing is just washing away information that I cannot get measuring energy, because I impose this thing. I can impose that other things other things can be conservative, other things can be preserved here. Then I have more information than just the energy. For instance, if I have an ion trap quantum computer, I can measure the state of the system, the qubit. This I can measure entirely, because I can simply do quantum state tomography of the qubit. But the vibrational levels of the ion I cannot measure. I just measure the energy, because it's a harmonic oscillator. I cannot measure correlations between these guys. But the state of the system, of the qubit system, has some information about coherences in the quantum harmonic oscillator. So I have more information than just measuring energy. And this is, is a straightforward extension of this theory. Then I just get things that commute with the Hamiltonian. I must impose that they commute with the Hamiltonian, because it must preserve energy. But then it's not just one observable, but several observables. This can be done, and it depends on what I can actually measure. This is why we call these thermodynamic group, and this makes a huge difference between these and the symmetry groups behind the physical theories. Because the symmetry group behind electrodynamics, for instance, is a fundamental one. There is no way you can do in order for you to measure the potentials, to get the information that is there in the potential. There is no way. This is the fundamental symmetry of nature. This is not. This is a symmetry that emerges from my limitations on getting information back from the system. That's just this, which is usually the real thing. So it's a gauge. Is a gauge group, it's a symmetry group on the space of information. That I'm throwing away information depending on what I can measure and what I cannot measure. And then I just I mean, it's easily to prove. It's easy to prove that the usual definition that I showed very at the beginning is not invariant of the works, not invariant under the deduction of this group. But the invariant work can be written like this. I mean, just replacing, just computing this quantity here. You can show that it's equal to this guy here, right? This U is this H is the diagonal Hamiltonian, diagonal form of the Hamiltonian at time t, and this U contains the eigenbases of the Hamiltonian. So work is related to the tangent eigenvalues of the Hamiltonian. That's Q. Q can be written like this. Q usual because this usual is the usual form that we see in textbooks or in papers. The change in this guy, and this is just the Hamiltonian of the system. But here we have a different part. We have this guy that relates to the changes in the eigenbases of the Hamiltonian. So this is fundamentally linked to the contributions coming from a generation of coherences. So you have a process that is changing the basis of the Hamiltonian and is inducing the creation of coherence, quantum coherence between the system. And why this is huge? Well, because if I can only measure energy, eigenvalues, I cannot access coherence. So the energy that I'm just wasting energy creating coherence that I cannot get back because I cannot measure quantum coherence. That's why this is huge. That's why it appears here. So it's just about how much information I can get back from the system due to a limited set of measurements that I'm able to perform. And the entropy is this guy. The entropy is a little bit more difficult to compute, but it's just the von Neumann entropy of the average stage over the group. Since the von Neumann entropy is invariant under unitarity transformation, we need to average the stage and then put it here. So that's the thermodynamic entropy that emerges from this theory. And this is very interesting, actually, because it turns out to be exactly an entropy defined many years ago. This is in this paper, the calculations are in this paper. It's a 20 pages paper with all the calculations there, if you are interested. But in 1957, a guy called Janis published a paper where he used Shannon entropy and a second paper where he used von Neumann entropy to derive the entire statistical physics. So he derived the statistical physics for information theory. And the entropy that he got there was a thing that called diagonal entropy. And this entropy is exactly equal to diagonal entropy when I have no degeneracies. Like a harmonic oscillator. It's going to be exactly the diagonal entropy with an entropy that appeared in 1957. It has all the properties that a thermodynamic entropy should fulfill. This guy increases for every process. Every one. Except for adiabatic one, which are those that doesn't cause transitions in the energy eigenbase. And therefore doesn't create coherences, and I do not lose information. So this guy is simply, that doesn't change. And when I have degeneracies, then these guys are bigger than 1. These n are bigger than 1, at least one of them is bigger than 1. And then we have what we call observational entropy, which is a sort of coarse-grained entropy because we are doing coarse measurements. Because degeneracies, we cannot access degeneracies. We can only measure the eigenvalues of these guys. So the degree of degeneracy should contribute to the entropy, and this is equal, and this will lead to a diagonal entropy plus a term that depends on the volume of each one of these degenerated subspaces, which is Boltzmann entropy. So the theory makes absolutely sense, and is absolutely compatible with what we expect from a thermodynamic sense, and is fundamentally constructed on a fundamental principle of physics, which is gauge. A gauge principle, but applied to information space. And we have everything that we want. And if I define this new quantity here, use the guide that diagonalizes age, then I can define this quantum channel. This is the channel. And then the entropy can be seen as the entropy of the channel. The thermodynamic entropy is the entropy of the channel. That does this thing. And this guy is a symmetry. It's a symmetry transformation. So we can study how much the channel breaks down symmetry, and to see, and that is a line of research where the guys studied informational quantities to quantify symmetry or break down symmetry actually. So we can apply these tools to understand that, to understand how inefficient a process is, an information process is, given by how much he breaks down some symmetry that you are interested in. Like here is the time translational symmetry. Time reverse symmetry. So this guy breaks time reverse symmetry. And also this is, for all process, this is bigger or equal to 0. The variance of this guy will be positive or 0 at best, which is what you expected from a thermodynamic entropy. This is just a thing that I'm developing now. We can define this covariant derivative based on this holonomy here. And then we can write the invariant heating work like this. But now, in order to actually establish a gauge theory, we needed to prove a technical detail that's quite hard. That is, these guys related to the connection of the principal fiber bundle. Okay, I don't expect that you understand this, but it's a technical thing that if you do this, then you have a proper gauge theory. The mathematical structure of a gauge theory. But we didn't do this yet. I actually don't know how to do. Hopefully some PhD students will understand how to do. But for now, I don't know how to do this thing. And that's it. I mean, we have, yeah, I almost done it. Based on a gauge principle applied to the information space, we're able to define thermodynamic quantities, and also we can actually generalize this theory to other quantities. That it doesn't matter to thermodynamics. It matters to anything that we want. I mean, you can just change the observable that we're measuring and compute other quantities from this guy, giving a limited access to measurements. That's the main point. I mean, given that I'm not able to perform any measurement, so von Neumann entropy doesn't matter for us because I don't have access to all that information. But what can I say about physical quantities? And then we give a recipe to compute these physical quantities. We apply to thermodynamics, but it can be applied to anything. Because it's just me, I'm limiting the amount of information that I can get from the system, and then what can I compute from this? Of course, if I change the observables that I am interested in, the group will change. But I hardly doubt that the isometry of that U group will change. I would be very, very scared if this happens. But I don't think that this will happen. Just will be a more restricted set of transformations, but they'll be there. But when we only have a measurements of energy, then the theory is there. And we can define it whatever we want for these things. And question, guys? Oh, the microphone.
The notion of entropy that you define, that in the end, in the conclusions, you mentioned that it always increases under any operation.
Yeah.
Yeah, I don't see. Why is that?
Sorry?
Why is that? How do you prove that it only increases under any operation?
Oh, because of this. Because of this. this is equal to this guy here, which this comes out from here. We just put von Neumann entropy here. Because von Neumann entropy is the entropy that we have, is the one that characterizes the information that I have. I apply group average, I'm getting rid of the information that I cannot get back from the measurement.
But you're getting rid of that information to compute the entropy. But then the state that you evolve is the original state, the one that there is in the system, right? No.
Oh no. The system, I'm assuming that the system is being evolved in some under some Hamiltonian or master equation or whatever. The system is evolving. I have rho of t. In the system has the state there.
Yeah.
But I assume them. No, I cannot get back all this information because I can only measure energy.
Sure.
I cannot measure anything. So how can I get rid of all this information that I actually will not have? Gauge average like this.
Yeah.
But von Neumann entropy is invariant under unitary transformation. So I need to apply this thing.
Well,
I'm averaging the stage of the system over the entire group of symmetry, which means that I'm considering all the states in the subspace linked by this group of symmetry that gives me the same amount of average energy. So I'm averaging over all these states. And this is the information that I get because I can only measure energy. I cannot measure anything else.
But you first average the state and then compute the entropy?
Yeah,
or...
exactly. Then I put the average state into the von Neumann entropy.
Yes. But then now this state evolves and your statement is that...
I do this at every instant of time.
Yeah. But then if the original state evolves and you compute this entropy again...
Yes.
Your claim is that the entropy can only increase.
Exactly. And this
Okay,
statement comes from this. Because when I computed this thing, I just defined this thing here. This is the output of this averaging process that we just discussed. And what comes out is that this guy is equal to this guy, and you prove that it is equal to observational entropy and diagonal entropy for non-degenerate states.
Yeah.
And these guys, we know for a long time that they only increase.
Yeah, but because they are in a non-degenerate.
No.
Right?
This guy includes degeneracies.
Mm-hmm.
Observational entropy includes degeneracies. When degeneracies are zero, which means that these guys are all of them are equal to 1, then this guy reduces to this guy. But we know for a long time that this guy, they is observational entropy, and this guy always increase. So I actually didn't. It wasn't necessary to prove that this guy increases because it was already proven.
Okay, then there is something in the definitions that I'm not understanding. So
okay.
Maybe I will ask you later.
Sorry?
Maybe I will ask you later because there is something in.
You can ask now. I mean, we are here.
Yeah. Okay. There is something in the definition.
You want to go to lunch? Okay.
No. I'm fine. If people is fine, I mean, if there are no more questions, I can keep on asking. I just don't want to. Okay. So there is something in the definition I'm not understanding.
Which
then.
definition?
Of the average state. The state after you do the average of the group.
This.
Yeah, that state is like you have the different blocks corresponding to different eigen states of the Hamiltonian, right?
Exactly.
And in each of them, it's like the identity maximally mixed within each subspace, but they have different weights,
not
right?
the identity.
What do you have?
Not the identity, because look, if I write the stage, this stage, in the energy eigenbasis, this average will not change the diagonal. It will only kills coherences.
It kills coherence.
Yeah, it kills quantum coherence in the energy eigenbasis.
Okay.
Because this is the information that I don't have access.
Okay, so
because I cannot measure other things except the energy. So I must throw away this information. But the diagonal part of this guy in the energy eigenbase, that's the meaning of this E here. It's in the energy eigenbase. Doesn't change because V commutes with the Hamiltonian. So they are diagonal at the same base.
But I think that the Céleri is negative because this is a EHU lemma. For every subspace is identity. But in every constant that you have in the identity is not the same.
Oh, well, yeah.
But you have an identity in each of the blocks, right?
Of course. Yeah, because each one of the subspaces is proportional to the eigenvalue
Sure.
associated with the.
Yeah, that's it.
Yeah.
Okay,
And you
okay,
have a block that's dimension n.
Okay, then. Okay, let's say there is like a very big subspace.
Okay.
In the original state, there are only the original state is only of rank 2, but this subspace is super big.
Okay.
Then you will assign an observational entropy that is much larger than the actual entropy that the state has. If you were able to know that it is only rank 2. Once you do this,
Well, but when you call observational entropy will be big here because you have a bunch of states that can store information, but you cannot have access because of degeneracies. But
Yeah.
when you say that information is small, is the von Neumann entropy.
yeah,
Oh, this can be zero. This can be zero. If
Yes.
the state is pure, it's zero.
okay, then let's say the state is pure. But now if I do an operation that moves the state out of that subspace to a subspace with dimension 1, then I am decreasing that entropy that you defined, right?
Yes, it's increasing. Exactly.
Okay, then what kind of operations preserve this entropy that you defined or only increase this entropy that you defined?
What kind of operation?
Operations, yeah.
Any quantum operation. Any completely positive and trace preserving.
But I
method.
just told you an operation that decreases it, right?
No, it doesn't decrease it decreases von Neumann entropy, but not the observational one. This cannot be.
You see, I'm not understanding something there because I don't see how it doesn't decrease.
Okay. I think I got your question. This is the second law of thermodynamics, which means that closed systems, an operation that you just mentioned cannot be done and performed in a closed system. Entropy can decrease. Thermodynamic entropy can decrease if the system is open. And a simple example is just an excited atom that is in contact with the vacuum of electromagnetic field. In certain sense, it will decay, and the entropy of the system, entire system, increases because of the huge amount of modes that the electromagnetic field has. So the uncertainty increases a lot. But the entropy of the atom decreases because now it's the fundamental state.
Mm-hmm.
You see, this statement holds only for closed systems, the entire system. Because if the system is open, then anything can happen. Yeah, I should put
you
it
mean
here.
Closed?
Yeah, I should put it here. That
But
closed system.
then means that you only allow unitary operations,
Unitary
and the operation that I mentioned is unitary.
But how do you do this operation? Come again, please.
Can I go to the board maybe
Of
and
course.
explain? I mean, if anyone has any question, please just. Okay, so I mean,
this
let's
one.
say this one.
This one, because the other one is bad.
So this is like the situation that I mentioned. So this is like a big subspace.
Yeah.
Energy subspace, and this is only one.
Okay.
Now let's say that our state is 1 here and 0 everywhere else, but then the entropy that you assign, you cannot read this detail here. So here what you see is a huge identity, right? For your entropy.
Yeah.
Okay, but now doing a unitary operation, I can move this one to this position.
But what do you mean by like this.
Doing a unitary operation on the system, I can move this this eigenstate or this state
Excitation.
to this excitation. I can move it to this ground state, let's say.
Okay.
I can do this with in a unitary manner.
Can you? Yeah.
Huh?
Exactly.
Yeah, but what's the
They have
problem?
different
This is a
eigenvalues.
unitary operation.
No, this is exactly the example that I gave to you. Let us suppose that this guy is an excited state of the atom,
Yeah.
but there's a huge degeneracy in the angular momentum, which I can have.
Yeah,
And this is the ground state, which no degenerate.
yeah.
To go from here to here, I have to induce decay, which is not unitary.
I mean,
Yeah, I cannot, because they have different eigenvalues. I must exchange energy with the outside. You see?
yes,
Yeah. It
but
is open.
yes, but the operation that I just mentioned is unitary also. So what you mean is that this entropy can only increase under the evolution of the Hamiltonian, right?
Yeah, but I'm not understanding why is this unitary?
That's just
Otherwise, you know,
it's,
a bunch of things.
it's a permutation of two columns.
Oh,
So it's
not-
just the unitary operation.
Yeah, not really, because they have different eigenvalues.
Mhm.
Energy eigenvalues are distinct.
Yes.
So you must change the energy, you must open the system. The Hamiltonian must be time dependent. Otherwise, you cannot do this. It can be unitary, but it must be time dependent.
Yeah. Okay.
I mean, like the example that I gave to you, the electromagnetic field in the atom, the total unitary is the total evolution is unitary, but entropy increases. The global system, but the entropy of the atom decreases because you did something like this, but then you did some other thing in the field that's much worse than this. I'm just talking about spontaneous emission. This is exactly spontaneous emission. You're not satisfied, no?
No, but I prefer to leave the discussion.
We can
already,
discuss
it's
over
fine.
lunch. No worries.
Okay.